Hello, my name is Brian, and this is my lab four, Oscillations. In this lab, we tracked and observed and modeled using tracker and glow scripts, a ball slash an object hanging by a spring, and just kind of oscillating both in the horizontal and vertical direction. And yeah, we're going to look at that motion in this lab. The initial conditions slash constants, a lot of these were given to us either by the pre-lecture videos or I guess by people who did the experiment in person. The mass of the object or the ball was 0.402 kilograms. The initial position, as observed in the video, was negative 0.113 comma 0.622. Obviously, this is relative to the fixed spring point, or I guess where the spring is fixed. Um, the where that is fixed is going to be 0, 0, right? And of course, the initial position is relative to that. The period length, if we measure it, it's around 1.638 seconds, right? The spring stiffness, K, you could calculate that by 4 times pi squared times mass over t squared, or the period length squared, and we got around 6.085 newtons per meter. The extended spring length given to us by the video was zero point 0.7 meters, and the relaxed spring length, if we use a spring formula or Hooke's law, we get L naught is equal to 0.052 meters. So yeah, given these conditions, we obviously want to also take a look at the physics fundamentals and the principles behind everything. For this lab, at least, obviously we have Newton's laws, right? We have the forces, Fg equals mg, gravitation, right? The gravity that's holding the ball downwards. We have the spring force that's attached to the ball, right? That also exerts a force. And in total, we have F net, which is equal to the gravitational force plus the spring force. And then once we find our F net, we are also allowed to update our velocities and our positions. According to Newton's second law, we could find the final velocity, or I guess the next velocity, by adding the net force divided by the mass times delta t. You can also add that to the initial velocity, and then yeah, the same could be done with the position. The energy principle kind of states that unless heat is released, there's really no change in energy in a system, right? In a balanced system. And also we have that UG energy due to gravitation is going to be mgh on the surface of the earth, and energy due to spring force is going to be equal to 1/2 ks squared. All right, so let's just jump right into the code. Obviously, we have our constants here on the left. We have our spring constant and then our relaxed length of spring. We also, from these two, we are able to find I guess, the vector L, right? In which that describes, I guess, how long the spring is and while the ball is in motion, right? Obviously, we calculate that by the ball's position, subtracting the spring position, right? And then we're able to get S by getting the magnitude of that and subtracting the relaxed length, right? In order to find our spring force. And then over here, down here on the left side, you can see the energy. This is no different from the energy formulas, for kinetic energy, gravitational spring force, and total energy in general. All right, in the calculation loop here on the right, essentially in every single iteration, we were able to update the forces, gravitational spring and Fnet, and simultaneously update the velocity and the position of the ball for the model, right? Of course, for the spring, we updated the spring whenever we could by applying the same Hooke's law, applying this Hooke's law to this to update the spring length. Right, and that's pretty much it. And yeah, I could pretty much show you what goes on here. Yeah, so the spring, here's the model for the ball attached to the spring. As you can see, the values that were derived straight from tracker and put into a CSV is very similar to the values that were shown in the model. Uh, if there are any differences, it is because there's air resistance, obviously, when the people were actually conducting this experiment, and yeah, they're definitely that definitely explains a lot of the differences. Also, any tracker errors, any human errors when tracking, that could also contribute to the differences. But yeah, uh, so yeah, essentially, what does it mean? Is the energy principle satisfied? I think that's one question that we want to ask, and the answer is pretty much yes. If you guys can take a look at this energy versus time graph, or at least change in energy versus time, we all know that delta E has to equal zero because unless heat is released, energy within a system is always going to be constant. And as you can see, if you were to take the areas or take the integrals of zero to whatever, it's going to equal zero, right? And yeah, total energy of a system remains constant, and change in energy is always going to add up to zero, which makes the energy principle satisfactory. And I guess another thing we calculate is the oscillation period. The x duration is around 1.61. If you were to go back to the model here, right? If we were to count the little peaks or the troughs, is around 1.61 for the x direction, and in the y direction, it was around 1.5 seconds. Obviously, the x direction is a little bit longer because the spring's range of motion it was very elliptical, and there was more variance in the x direction more than in the y direction. So of course, it's going to spend a little bit more time in the horizontal phase or making a horizontal loop than a vertical loop. All right, thank you. That was mostly it.